In the second part, we will look at circuit simulators. I use the free LTSpice4 program because there are no limitations on the number of components, and you will find good tube models and tutorials on the internet. In the post problem, in the final exam, they used the basic theoretical model of Scott Reynolds and Marshall. For the triode tube, there exist some more complex empirical models which try to copy the datasheet curves. I use the Norman Korn tube model for my simulations. At Digelander you will find a lot of different tube models and also library files to use with your simulation program. This is the result of the calculated signals from the exam. One of the questions was if we could regard the input and output capacitors as shorts for the audio signal, which was 20 Hz to 20 kHz. So if we calculate the minus 3 dB breakpoint frequency, we have for the input a 1.6 Hz and 0.2 Hz, so this is well below the 20 Hz of our audio signal we want to use. The amplification of the circuit is minus 8.7, so a 1 volt input signal will give 8.7 volt output signal. It's very easy to draw the tube curve with this model in Excel. I have drawn here the static load line, which gives us a plate voltage of 68 volt, a plate current of 1.7 milliamperes, and a grid cathode voltage of minus 1.7 volts. For alternating current, this capacitor will be a short, so the load resistor R3 should be added to calculate our load line. So the dynamic load line will be a bit more higher at 6.5 milliamps than the static load line. So let's look at the LTSpice files. So in this circuit you see I have added a power supply, which is a copy of my test power supply I will use for the practical demonstration. We have here a variable transformer, a bridge rectifier, and a RLC filter. So this coil has a high internal resistance, which add to the characteristic of the filter. And this will give us a DC voltage of 100 volt here at VBB. For the bias voltages on the gate, we will use no input signal here. The tube model we use should be added in the as a SPICE directive. So if we look here, so we have to include the current tubes.inc file. We set up a transition analysis with a stop time of 6 seconds. So, and this results in a curve here. So this is the power supply voltage. Show some ring. This is caused by the filter. It's 100 volt. We have 0 volt input voltage, a 1.7 volt cathode voltage, and a 60.8 volt anode voltage. If we add here alternating current at the input of 1 volt, we will see the signal amplified at output. So this is the 1 volt alternating current, the red one, and the yellow one is the amplified alternating current. So this is -8 to plus 8 volt. So an amplification factor of about 8. This is the anode voltage. And the power supply voltage stays at 100 volt. For the frequency analysis, we have to first put here in the input signal here a function on, and here a small signal analysis, AC amplitude of 1 volt, and SPICE directive, AC analysis, type of sweep octave, and we will make a sweep between half hertz and 500 kilohertz. In the resulting frequency response, we see here a breakpoint at about 2 Hz. So this is -3 dB. Also a small phase shift here until from 20 to 100 Hz. So normally we have a 180 degrees phase shift because it's an inverting amplifier. At the high side, the 20 kilohertz is very good.